In 2016, this quantum setup started shocking the foundations of physics. I wanted to understand why.
You can accurately say I have an error 1/12 of the time.
Yeah.
But you cannot predict when you get the error.
Correct, yes. I mean, yes, yeah. It's teaching us that like the way we're using quantum mechanics is kind of breaking down at this level.
What if you spend 11 hours in a completely logical world? But then, exactly between 11 and 12, logic breaks down.
So Bob got one, so Alice got one, so I must have gotten fail. But look at my measurement outcome. I got okay.
This is Physicist Dr. Lídia Del Rio explaining to me the Frauchiger-Renner thought experiment that predicts a strange quantum paradox exactly 1/12 of the time.
What we used to call facts, which are observations, are not absolute.
With one observer, quantum mechanics leads to the strangeness of the measurement problem. With two observers, you get the Wigner's friend paradox, which is highly mysterious but doesn't break down the theory. That seems to happen when you get to a setup with 4 observers. Now, all of a sudden, quantum mechanics seems to be playing Russian roulette on itself.
This is like physics entering philosophy, and as physicists, we are very unprepared. You cannot have both like this outside view and know what people are experiencing inside the experiment.
I can give you Super Mario on a disc. Here's the game, and then
right.
there you have it. That's the universe. But we both know that the game is to be played and to be in it and to have these different perspectives.
Yes, yeah. It's also one criticism that many of the shut up and calculate kind of physicists say of this is like, yeah, you should not be allowed to take the point of view of these little agents inside their boxes. Like, just apply the Schrödinger equation from the outside. You see everything evolving like beautiful.
Yeah.
But we are the little people inside the boxes.
Yeah, exactly. No, that
right?
doesn't tell us anything in the end.
We are not experiencing the video game from the perspective of the developer outside reading the code. We are inside the game.
The famous quantum physicist John Wheeler once said that physics used to look at the world from behind a thick plate of glass, but that quantum mechanics broke the glass, and that as observers we had to reach in to accept the fact that we have a participatory role to play in our universe. This conversation is exactly about that. This conversation consists of 3 parts. In the first part, Dr. Lídia Del Rio and I discuss the necessity of modeling observers in quantum mechanics. In the second part, we have a deep dive into the Frauchiger-Renner thought experiment. And in the third part, we discuss the meaning and implications of this thought experiment. Now, before we start, I would really want to thank Lídia because she is 6 months pregnant, but still took all the time to explain this profoundly weird quantum experiment to me. I hope you enjoy it. Welcome at the Essentia Foundation's YouTube channel. I'm very thrilled and happy to be sitting here in the Netherlands with Dr. Lídia Del Rio. Lídia, warm welcome in the Netherlands.
Thank you for having me.
Nice that you're here. You were sort of in between traveling to Bristol where you also had some work to do, right?
Yes, I had a thesis defense there.
Yeah, and you are research fellow of the Essentia Foundation and a senior scientist at the University of Zürich, where your work focuses on quantum information theory and in particular on how to model agents as observers, or to model agents and observers as physical systems. I always like this quote by John Wheeler where he says that we used to look at the world behind a thick plate of glass, sort of us, the observer, safely behind the plate of glass. And that after quantum theory, the glass is broken, he said, and we have to reach in. So it's sort of this border between object and subject, the object-subject divide isn't there anymore. Is that a way to understand it? Do you like that metaphor, or how do you sort of explain it to students who are new to this?
So I like the metaphor. I don't think it's only in quantum theory, but maybe quantum theory makes it more unavoidable to see this issue that we cannot just take ourselves out of the picture.
Yeah.
I mean, somehow it's something that's very natural in social sciences. or even in journalism, right? When I go to interview someone, who am I as a journalist? Like, what is my position going to be, and so on, right? Or like, can I ask questions about something that I really care about, and like, what's the boundary between activism and journal, like all these things, right?
Exactly.
And in physics, indeed, in many areas of physics, we can kind of safely stay behind this glass pane. Quantum theory is one example where this is really breaking down, and we see that no, there's problems if we cannot just keep this view.
The way to distinguish between observer and observed, sort of that, what in quantum theory is called the Heisenberg cut, right? Where you say, where does sort of the quantum reality become classical in a defined state? Where we put that cut, that plate of glass that Wheeler says is smashed, is it now completely arbitrary?
Yes. I mean, you can put it wherever you want, and then you'll get different results depending on where you put it. Right? So one example is, let me look at the hydrogen atom. There's a proton in the middle and an electron going around it. If I treat the whole thing as classical, then I will not get the right results for the behavior. If I treat, there's a classical particle going around, feeling some electric force and going around this, then I will not get the right results. If I put the Heisenberg cut just around the electron and say, okay, I'll treat the electron as a quantum system, but it's too complicated to also treat like the nucleus of this atom as a quantum system. So I just say there's a quantum particle that feels an electric potential, right? Then I can get pretty good results, quite accurate of like for the behavior of this particle that then match measurements.
Yeah.
I could go one step further and say, okay, now I also want to treat the proton. I treat the whole thing as quantum, so these are two quantum particles. Then the calculation becomes much more complex. And, depending on how deep you go, then you might get some corrections to your previous results, right?
Yeah.
So to some extent, there's some freedom.
Mm-hmm.
And then what some new results show us is that there could be incompatible ways to put the Heisenberg cut, in which if we do put the Heisenberg cuts in different places, then we can reach contradictory conclusions, which would mean like, there's not like a single experience of a reality for the two of us. This is really it's really just not compatible.
This is where it really gets cool. And also, we're not there yet experimentally, right? Because now we're talking about thought experiments in quantum mechanics. Mm-hmm. And I think Eugene Wigner was one of the first physicists to really bring this up, sort of this, where do I put the cut, right? Because, how would you explain his thought experiment, so the Wigner's friend experiment?
So it's kind of going one step forward from Schrödinger's cat.
Mm-hmm.
So Schrödinger's cat, you have a cat in a box, you do some quantum, particle can decay or not. This generates a chain reaction that ends up in a macroscopic change, right? The cat can die or not, but if it's in the box, if you're looking from the outside, you still see the cat as being in a superposition, right?
Yeah.
And Wigner is like asking, okay, what about the cat's perspective? So instead of a cat, now we have a person in a box. Let's call her Alice. And Alice is measuring a qubit, a small quantum system, an electron spin or a photon polarization, whatever. And so from her subjective experience, she sees one outcome, because this is what we do when we go to the lab. We do the experiment, see an outcome. From the outside, if Wigner treats like the whole of her lab as an isolated quantum system evolving, there's no collapse from his perspective. It was all a reversible evolution that happened. So Wigner sees her as being in a superposition of seeing one outcome in the other outcome, right?
Yep.
And this seemed to be like a little bit, maybe a bit incompatible views of nature, of what's going on. This already tells us that we were used to conflating observations with facts of the world. So for example, I measure an electric current, or I measure the height of a tree, and this is a property of the tree. Of course, Einstein's relativity already challenged this a little bit in saying that, a distance that you measure depends at the speed at which you travel. But still, like, if I have someone else traveling together with me, we'll see the same.
Yeah, then it's check again.
Yeah. And you can, like, transform this to some property of the tree I'm measuring, right?
Yeah.
Still, anyway. Good. And what quantum mechanics, and in particular this experiment, tells us is that, no, this is not the same. The fact that you observed something that is a subjective experience, a measured outcome is not a fact of the world, it's a relational thing between you and the world that is not seen like this from other people's perspectives. What quantum mechanics tells us is, look, so I'm making a measurement. I'm measuring a spin of an electron. How do I do this? Classical example, I do this Stern-Gerlach experiment where there's an electron coming. I put some magnets here. It goes through a magnetic field. Then, depending on the spin of the electron, it goes up or it goes down. If it started with well-defined spin up or spin down. If it starts in a superposition of up and down, what is happening is that now I'm correlating this kind of position degree of freedom, meaning like, the speed of the electron, which direction it goes. I'm correlating this with the spin. Right? So now it's like, it's a superposition of spin up and going up and spin down and going down.
Yeah.
Okay. Then this electron hits a screen. And we say, oh, we measure where the electron arrived. But in reality, what's happening? I don't know. Maybe there's some photoelectric effect going on here that then releases some photons. This is also a quantum process, right? So here we have a superposition of spin was up, electron went up, excited some atoms here, photons released here, or down, it went down, da-da-da, photons released here. It's still a superposition. There's not one single outcome. It's like this thing that could be, if I put now a mirror there and there, and I have much better control than I actually have, then maybe I could reverse the whole thing and come back to an electron here. Yeah.
But this to me is like new in the sense that it seems like when a particle hits the screen in this Stern-Gerlach experiment or in a classical double slit, I always thought that sort of when it hits the screen, we're collapsed and we have a definite outcome. So that's
from your perspective, because this is when you perceive it as thing. But what's happening now? Okay, now photons from here and here are coming to your eyes, right?
Yeah.
And this is still a quantum process. Whatever is happening inside your eyes, these are atoms and molecules interacting. It's still a quantum process, right? But somehow, and that's a miracle, we have the subjective experience of seeing just one of these things happening.
Yeah, okay.
How does quantum mechanics explain this? It's actually very nice. It's just saying that, this photon is not just getting correlated with like a few things. There's like all this environment around it. And as soon as like you have even if you have this reversible evolution, as soon as we ignore part of the information, what is called tracing out in quantum mechanics, as soon as I lose track of some of the environment, then it appears to be a classical mixture. It appears to be one thing or the other with some probability distribution. So the perspective we have is a subjective thing. Like you say, okay, it's when the electron hits the screen that the collapse happens. And what this translates to is like when the electron hits the screen, this kind of information is kind of spread out. There's interaction with so many particles in the environment that we don't keep track of, our eyes don't keep track of, and therefore we see one thing or the other. Right? But from God's view or super observer's view, it's still all a reversible process, and there's not a single outcome. You just see a single outcome when you just start losing information, and losing information is not an objective thing; it's a subjective.
Losing information is a measurement, or
essentially, like the moment when you stop seeing a unitary evolution and you see a single outcome is because you traced out something, you ignored something, because the world is.
I think people listening who are not physicists and people on the street will say, okay, maybe you're right, but you're making stuff now so abstract, philosophical even. How is this practical? I love it actually, because you say you have to look at the whole picture here. You cannot just say exactly what you're saying. Quantum effects are taking place in my brain. So the moment I measure, if I want to have a physical theory that sort of takes account of all of that, I have to take steps back, right? And of course, there's a limit to what we how many steps we can take back.
Yeah.
But yeah, sort of my initial sort of not critique, but just is that it just sounds so abstract. How is that on earth practical, or how can we put it to tests? But that is exactly what you are doing with these thought experiments, right?
Right. Yes. Yeah.
So there you say, okay, now we're not going to treat a particle hitting a screen as an outcome, because we're going to take a step back.
Yeah.
We're going to look at who looked at that particle hitting the screen, and we're going to trying to model that agent, right?
Yeah, that's right.
Okay,
yes.
and how do you do that? How do you model agents?
Okay. So I'm not trying to like simulate brains or try to model all of you. We just like go to the most minimal thing that we can do.
Okay.
Okay, and this is treating again a measurement as just entanglement between. So I'm sorry for the word. There's no good. I have not found a good classical analogy, precisely because it's a new phenomenon, right? But it's like a measurement is two systems, which is like the system I want to measure and the observer getting correlated.
Yeah, and that's we call entangled. So now I'm entangled with.
Yeah, so now I'm entangled with this in this thing that could be reversed in principle, but because usually these systems become so big and complex, like nobody can reverse it.
Yeah.
Right? Okay, so we have, and now the question is like, okay, how small can I make these systems and still have this phenomena? And how small is like essentially 2 bits. 1 bit for the system I'm measuring and 1 bit for, say, the memory of the observer, where, like a notebook where the observer writes the outcome. Okay.
Yeah.
Of course, not classical bit, quantum bit, but still like a 4-dimensional system, so very, very small. Then, so we need to have a few more things, like agents don't just observe things, but they make decisions based on their observations, right? You can say, if I look outside and I see clouds, or rainy clouds, I'll bring my umbrella out. If not, right? And all your decisions you can kind of trace back to an observation.
Yeah.
Naively speaking. Okay, so we add a few more qubits, much like a simple computer circuit that you program and say, okay, if I measure X, then I do A. If I measure Y, then I do B. So we can still model this like in the same way that you could program a very, very simple, 4-bit program to do this. You can do the same with quantum circuits, and the difference is just that everything from the outside, everything is kind of a reversible evolution.
Yeah, when we talk about sort of just good to understand reversibility in quantum mechanics, what exactly are we talking about?
Okay, maybe we can talk about the simplest experiment. Say one electron is measuring another electron spin. Okay? Electrons have this property inside called spin, and it's measuring whether it's like spin up or spin down. And the way we model the measurement as a physical evolution is like these two things are getting correlated in a way that if this was up, then this becomes up too. And if this was down, this becomes down too, right? And for maybe people with classical computer science background, this is a C0 gate. So it's like a unitary gate that you can apply. So in practice, we do this by shooting some lasers at them in a way that, just correlates one with the other. Okay? Just like in knitting, you can take like 2 threads and you just correlate them, and you can undo this process, and now you have these 2 threads being separated. So in the same way, in quantum mechanics, you can shoot some other lasers at them and get them, like, do the inverse operation. It doesn't mean you're going back in time. Like, maybe from the perspective of this whole electron, yes, you'd be going back in time. But if I'm modeling a more complex observer, like maybe my brain is a bit larger than, maybe, 10 electrons inside, then I could have some electrons that keep the memory that there was a measurement, but the outcome of the measurement has been forgotten because I reversed this. I disentangled these 2 things. And
you can really get back to the initial state in quantum mechanics.
In principle, you can go back to the initial state, yes. And some very clickbaity articles call this reversing time. I mean, it's not time going back. It's really just reversing this physical operation.
Yeah, I've heard it a couple of times, the sort of reversibility in quantum experiments, and that it's relevant. And I still don't really get why it is important, but maybe without going too deep into it, you can explain why we need it sort of as a concept to understand these thought experiments.
Okay. Well, one thing is that it will be an ingredient in the thought experiments that we'll talk about later.
Mm-hmm.
So we need some observer from the outside to be able to disentangle again, the friend inside the lab from the system they observed.
Mm-hmm.
This is one thing. The other thing is that a measurement is kind of by definition an irreversible process, because you go from this quantum state of the electron spin that could be in a superposition of up and down to just seeing it being up or just seeing it being down. And there's not like one operation that is not measurement dependent that I could to go back to the initial state, right? Unless it's also, affecting my memory, and then you're looking again from the outside. Does that make sense? So the measurement is an irreversible thing.
Yeah.
The subjective experience of a measurement is an irreversible thing.
Yeah.
I cannot go back to not knowing.
Yeah, or it would be destructive, right? That's what I've read. Sort of, because then you have to take a step back. I have to really erase your memory. So it's a sort of destructive operation to get back to sort of
And it's also like this idea of a collapse, right? Like once I know that, once I'm following, I don't know, which slit the particle is going through, I cannot go back and consider it as a way of going through the two things. That's just...
Yeah, okay. And we need this for better understanding the thought experiments. Okay.
And the idea of like all these thought experiments, like also what is reversible or not is a matter of perspective. So from your perspective, you think you made a measurement, you see a single outcome. It's your experience. I believe that you experienced this. And from your experience, it's an irreversible process. But for me, from the outside, it's a reversible thing that if I'm powerful enough, I could, undo.
Okay, that's interesting. Okay, I think good maybe now to move on to the whiteboard and you explaining stuff a bit more in detail and also being able to sort of draw stuff. Let's just do that, right?
Okay. Yeah.
Okay. Cool, Lydia. Let's go. It's quantum one-on-one.
Okay. So
starting classically, right?
This is still classical one-on-one. Okay. So I'll tell you about thermodynamics.
Yeah.
What do you think thermodynamics is about?
It has to do with entropy. That's what I get, sort of, that the universe moves from a low entropic to a high entropic state, and somehow miraculously we are sitting here low as a low entropy system. That's what I sort of
what you get from it, yeah.
From thermodynamics.
And I think that's what the idea that today there exists about thermodynamics is a theory that studies the world. And like phenomena going on in the world, heat and work and entropy flows and so on. It started actually much more operational than this. It started with, we want to make trains. We want to make heat engines. We want to take like this resource, heat, like I burn some wood, I have some hot gas, and I want to turn this into movement. So there was this idea of like heat is like energy, but energy that I don't control. And work is like a train moving, like energy that I can actually control.
Yeah, check.
Now, given our initial conversation, we can already see that these are subjective kind of concepts. And so here is an example of this. So then with time, like, although it started with these very kind of practical purposes, then it became more of a theory about, the world, how, a thermodynamic processes go on in our cells or in some natural thing we observe, or when we put two materials together, what's the heat flow like? It looks like a very objective thing from the outside. Yeah. And then Maxwell came up with this thought experiment. Okay.
Yeah.
Let's start with the gas. What is a gas at a certain temperature? It just means like, from the beginning, people already knew like the gas was made of particles, right? And they're moving at kind of random speeds and directions. Yeah. So I'll write here like a small arrow if the particle is moving slowly, and a fast arrow if it's moving. But we don't see this, right? So all we know is some macroscopic properties of this gas, like the temperature, the pressure, the volume, right? Which all result from these microscopic quantities that we don't have access to.
Yeah, and I smell it equally in the room if it's a gas that I can smell, right? It's not just local that I only smell it.
Yes, no, it's kind of spread out here in this whole box. with gas, right? And one of the laws of thermodynamics, like one of the formulations of the second law, is like you cannot just take heat into work. You cannot take energy that you don't control into energy that you control. Normally you need like a cold gas and a hot gas. And now from this difference in things, then you can build a fridge or you can build whatever, right? Okay, and then Maxwell thought, okay, yes, sure, we cannot see the position and velocity of all these particles, but now imagine that there's no reason why someone couldn't. So imagine now we have like this demon. He has like microscopic vision. He can actually see all these particles. And this demon puts like a little partition here in the middle of the box and has a little gate. Okay.
Yeah.
And now this demon can kind of control when to open the gate or not. And he opens the gate if there's a fast particle coming this way or a slow particle going the other way.
Yeah.
Yeah. So after a while, what do we have?
He's separating the two gases.
We have all the fast particles here, lots of kinetic energy, and all the slow particles there.
Yeah.
Okay, so this means that this is, in practice, this is a hot gas, because on average the particles are faster, and here this is a cold gas.
Yeah.
So from a single temperature, now we created like two temperatures. Okay, so what does the demon do now? Well, it can, for example, try to extract work from here. So put some system of pulleys here, some bucket, and a hot gas will try to expand precisely because these are these particles with more energy can expand against this cold gas. So this thing moves, and this goes up, and now we have like, we lifted a bucket. This is in the same way that like dams work for production of energy, right?
Yeah.
You pump this thing up here in the Netherlands, so
Yeah, we do a lot of pumping here.
lots of pumping up,
Yeah.
which usually costs work. Like, look, I did it for free,
Yeah,
right?
yeah.
So I created work, energy that I can control from heat.
Yeah, the only sort of what I would say is that opening and closing the door would take some energy also for him to do, or?
In principle, not. I mean, not to the same.
Yeah. Okay.
Kind
Check.
of
So
normal,
that it's very much about sort of he just doing like with minimal work, separating
yes,
those two.
yeah.
And then you can extract sort of work from the system, which sort of basically gave you free energy.
Looks like he gave me free energy, right? And now at the end, so I have like, okay, now at the end, after this expanded as much as it will expand, I just remove the partition, I put it back in the middle, let the particles mix again, and then I go back here.
Yeah, and then
I do it again.
Yeah.
Perpetual motion, right?
Yeah,
So
yeah.
violated the second law of thermodynamics. Yeah?
Yeah.
So what's the...
Yeah, and in sort of entropy talk, sort of the initial state is high entropy, and the daemon is able to bring it back to low entropy and go back to high entropy. And
this already tells us that there's some issue with the notion of entropy, right? Because one way to look at it is to say, for us, the state has high entropy. But for the daemon, the daemon has perfect knowledge of everything that's going on here, right? For the daemon, it has low entropy. But if you just want to look at it from the outside and say, okay, why is this not a reverse, like not a reversible, but a perpetual motion engine? Why can I not repeat this forever? The solution is kind of bringing the daemon inside the theory. So instead of just applying thermodynamics here, I move kind of the Heisenberg cut of my theory. So I say, no, the theory should treat also this daemon as a thermodynamic system. So what's going on in the daemon? So he has to store this information somewhere in the brain or memory or computer of which particles are fast and slow.
Yeah.
Right? So this is like a hard drive that the daemon is filling in.
Yeah.
Right? If he repeats this a few times, then he'll have to erase this hard drive or buy a new hard drive. Then the hard drive is a resource, right? And then what Charles Bennett and Rolf van Douwer showed is that actually the how much it costs you to format this hard drive again is precisely the work that you gained here.
And that we know mathematically, that's just physics.
Yes, this is the physics. So these two things cancel out.
Yeah.
So this is an example of like, oh yeah, even in classical physics, sometimes we need to bring the observer inside the theory, otherwise our analysis just breaks the theory, right? The
Yeah.
theory does not apply just at this scale, and you need to really consider it.
Yeah, that's
That's
really interesting when I saw sort of that erasing information costs energy, and it's the same energy that is gained in sort of this free energy example. Yeah.
So another way to look at it, if you don't want to model the memory explicitly, is like, no, this is a state of low entropy for the daemon.
Yeah.
He's just transforming like the information in you. Like he had information and energy here to information and energy here. Yeah. And then at the end, he lost information about where all these particles are. Now, again, if he wants to repeat, then he needs to gain this information again. And this, again, costs work, right?
And if we now sort of make this sort of, I like this analogy. I think it's very good. It's very understandable. If we now make it quantum, what would sort of be the sort of the quantum version of Maxwell's demon?
I mean, one can do the quantum version of Maxwell's demon. And then there's funny things like a quantum demon can actually extract even more work than a classical demon, because you can have quantum knowledge of like, if his memory is entangled with these particles, not just classical correlations, then you can even extract more work.
Okay.
But maybe we can talk again about a quantum measurement and a
or
quantum
an analogy.
observer.
Yeah, that's better, I think. Yeah,
okay.
Cool.
Yeah. Okay, so now let's talk about quantum measurements a little bit.
Yeah.
And now let's think again. So I have Alice here, and she's trying to measure, I don't know, the spin of an electron.
Yeah.
Okay. And this thing is in a superposition of being up and down with different weights, which translate to different probabilities of seeing one outcome or the other.
Yeah.
Okay. So then let's say now she's inside her lab. So this is Alice. She's measuring some system. And now from outside there's someone else. And normally I draw the outside observers with hats. Okay, so this is Ursula. Wigner will show up later because we're building up to a bigger experiment, right? So what is happening here? So from the perspective of Alice, she's making a measurement, getting a single outcome.
Yeah.
From the perspective of Ursula, Alice is just getting entangled with this thing.
Yeah.
Okay?
Yeah.
There's no single measurement from her perspective. She knows that Alice is a single measurement, but the whole state is a superposition.
Yeah, it could really be both spin up, spin down. Yeah.
So I'll write this as a little circuit. Okay, so we start with like, this is the thing she's measuring, your thing. Here's Alice, okay? And time goes left to right. And now there's some operation here. So in quantum mechanics, this is a control NOT gate. It doesn't matter. It's something that in principle, Ursula can come here and reverse. Shoot some lasers at it, reverse the operation. Okay, and then we'd go back to the initial state.
Okay.
So Alice is kind of braiding herself with R. So far, this is what's happening from her perspective. From Alice's perspective, what's happening is something different. So if I use squares for reversible operations, then I can use, I'll just write it here, then I'll erase. Then I can use like this for measurements.
They're irreversible.
For irreversible measurements. This is like the traditional symbol. Or even like something like this that has a pointer that shows us what's going on, right? So from Alice, this is happening. She's measuring R. It's a irreversible thing. She gets a single outcome. From Ursula's perspective, no, there's a reversible operation going on. Okay, so now, so far so good.
Yeah.
I can make it a little bit more complicated.
Yeah, so Ursula can, when we say it's reversible for Ursula, it, because Ursula hasn't yet sort of performed a measurement on Alice. She hasn't performed anything, right? So
so it could mean two things, right? So one thing it means is that Alice puts the Heisenberg cut just around this particle. Yeah. Like in the Maxwell's demon, we're just looking at the box.
Yeah.
Whereas Ursula is putting her Heisenberg cut outside the whole thing.
Yeah.
Okay?
Yeah.
And for now, it's just a matter of perspective. I'm looking at it from two different points of view. Later on, yes, Ursula will come here and do some other joint operation that undoes what Alice did.
Yeah.
Is that okay?
Yeah, that's okay.
Yeah, okay. So now we forgot about Ursula for a while, and let's talk a little bit about reasoning, logical reasoning. Very simple. Okay, so we had another thing. We say that Alice, so she's measuring the spin and can get two outcomes. Let's call it 0 and 1. Is that okay?
Yeah.
And Alice says, okay, she has a second spin here that she'll prepare. Yeah, and Alice says, okay, so if I get my outcome to be 0, she gets an outcome, she prepares a second spin in some state up.
Yeah.
If she gets the other outcome, she'll prepare the state in what we call a superposition of being up and down.
Check. Yeah.
Okay, something you can do in the lab.
Yeah.
Nothing special about this.
Depending on her measurement, she prepares another particle
Yeah.
in a either defined spin up or superposition spin down up at the same time. Yeah.
Okay.
Yeah. Check.
Right. She sends a second spin to Bob. Who's Bob? So Bob is here inside his own lab. So now he got this second spin. Okay.
Yeah.
It's in some unknown state for him. Alice knows what it is. Bob doesn't know. Bob measures it. Again, up or down. Two outcomes can be 0 or 1.
Yeah.
Okay? So if he measures this,
It could be still both, right? Because the other one.
if it's this one, it can only be 0. Because it's 0 is up, say.
Oh yeah.
Okay? So if you do this, then B is 1 for sure. But this is a superposition of up and down. Okay, so if he does this, then B equals 0 or B equals 1. 50-50 probabilities. Yeah? From my perspective. Yes.
So yeah. I thought because the if A is 1 for Alice,
Yeah.
she prepares the sort of superposition.
Yeah.
So it could be both up or down.
Yeah.
So the only way to know for sure, the only certain information you can get from Alice's lab is if you measure a down, I'd say, right? Because that's if Bob sees a spin down, then he knows for sure it must have been the superposed.
This should be 0, sorry.
Yeah, check.
Yeah, this should be 0. Yeah, this should be 0. Sorry.
Yeah.
0 means up. And
Yeah.
Okay, yes, exactly. So there you go. So now the game is exactly what you said. So the game is now Bob doesn't know what Alice measured, what she saw. He just did this measurement, and now he needs to guess what Alice did.
Yeah.
Okay. So if you obtain 0, sorry about that before. So if you obtain 0, he doesn't know, right? It could be in this case, or it could be in that case.
Yeah, could be both.
Could be both.
Yeah.
But if you got 1, then for sure he knows that,
Yeah.
the only way for me to get 1, Alice must have prepared this thing. Therefore, Alice must have obtained.
Yeah, so if I got spin down, I know for sure it must have been 1 because that only the superimposed particle can give me a spin down.
Yeah.
Yeah.
Okay, so this is the reasoning. So if B equals 1, then A equals 1. Okay.
Yeah.
For a classical analogy, if this was not a spin and this was a coin, we can still do the experiment. So at this point, we can still do the experiment. So Alice flips a coin. If it's heads, she prepares a second coin in heads. If it's tails, she prepares a second coin by just flipping it, not looking at it.
Yeah.
Sends to Bob. Bob then looks at the coin. If it's heads, he doesn't know which one it was. But if it was tails, he knows that, okay,
Yeah.
Alice must have done tails,
Yeah.
right? It's the same thing. I just added replaced the coin with a quantum measurement so far.
Yeah.
Which will only be important later.
Yeah.
But this is the kind of reasoning that we think is very natural.
Yeah, and Bob so knows 2 things. He gets a particle with something he can measure, and he has to know how Alice reasons, right? He knows exactly.
Yeah.
He knows that.
Yes, we know this. Yes, it's not a
Okay.
adversarial scenario. Everyone knows the recipe for what everyone is doing. And now we can think like in this scenario, what is Bob's Heisenberg cut? Well, he's reasoning about Alice's outcomes, so he believes that Alice saw an outcome.
Yeah.
So for him, Alice is classical. He's outside the Heisenberg cut.
Yeah.
But of course, these 2 particles are quantum particles. So like his Heisenberg cut includes these 2 things.
Yeah.
Yeah? Can I add one more agent? Because now it's where it gets a little bit more complicated.
Now it gets if we put agents outside the labs, right? Also watching at Alice and Bob.
Yeah, so I'm building up to the Frauchiger-Renner experiment, which is an extension of Wigner's friend that was proposed by...
Yeah, we have 2 Wigner boxes here, basically, right?
Yes, we have 2 Wigner boxes, yes.
Yeah.
So Ursula is friends with Alice, and Bob is friends with Wigner, who is outside here. Oh. Okay.
Yep.
So now, after Bob did his measurement, sometime later, Wigner will measure this whole thing. Okay, so let me now draw the rest of the circuit of what's happened here.
Yeah.
So, Alice, depending on what she saw, so depending on what's on her memory, she did some operation on this particle S, okay? This is again a logical gate, just with quantum particles.
Yeah.
And then Bob measured this particle S.
Sorry, S is the particle.
S is the second particle,
Oh yeah, that's the particle that Alice prepared and
sent. Alice prepared
sent to
Bob.
I'm seeing. S is sent.
And then Bob measured S, which seen from the outside, if I'm look at like perspective from the outside, from us, it's also some kind of operation. It's also this control gate that can be reversed in principle. Yeah? Good. So this is what it is. This is the whole circuit. And now Wigner is going to come here and do a big measurement on both the lab and this, which in practice corresponds to something that undoes this measurement and then does some...
This is really funny. This is a new way for me for looking at it when you put it like this in this logic gate, or what's the way to say what you're doing here with putting it in these lines?
Yes, I'm putting it like a quantum circuit. I'm designing it like a quantum circuit. Yeah, sometimes it's very helpful too.
Yeah, makes it sort of, at least so far, I think I still get it. Yeah.
So if we give names to these operations,
okay,
so let's call this, it's an operation U, which is a C note. This I call it V, it's a controlled Hadamard, if you want to know this, again U, and this is kind of U minus 1, it's the reverse of these two things. Meaning if I do this and I do that, this is the same as doing nothing.
Okay.
It's the identity, so it's like I go, you know, like you're watching a movie, you go skip forward, skip back, you end up in the initial state, okay?
Yeah.
So Bob did this, Wigner does this, and then he does a measurement here, okay? Which is a different measurement than what Alice and Bob were doing. Okay. But it's a measurement such that, and now is the part where, where if the initial state of this particle had been this, okay, where if we had like A equals 1, then Alice prepared S in this superposition, which then got kind of entangled with Bob's memory. And I'm trying really hard not to draw any formulas, so let's just say like they're entangled, like a braid. Yeah. And then Wigner does this thing. And what the math tells us is that if he does this measurement, then he'll always get some outcome, which for the purpose of this experiment, they call this outcome, they labeled it fail.
How?
Fail. Like,
fail, yeah.
Like succeed or fail.
Yeah.
And the measurement outcome is fail. Okay, but we could call it 0 or 1, but fail is more. Okay? So, this is kind of the, without formulas, what would happen? It's just like this entangled stage that is happening here, that we have here at this point.
Yeah.
If Wigner does all this, and we had started off with the S that Alice prepares if we had 1,
and
then he always gets the same outcome.
Yeah.
Okay.
Always get that outcome. Okay.
Always
For me,
gets that
I guess,
outcome.
okay, if all of this happened, he will always get that
He
outcome.
will always get
if
this
Alice
outcome.
prepared sort of...
If Alice prepared this from Alice's perspective, right? So which means that now Alice, what is Alice's Heisenberg cut? So now she's treating I mean, all of this as a quantum system, and R, of course, yeah. Because he needs to think, Bob thinks he's making a measurement, but he's just really getting entangled with S. I don't need to think about Bob's outcome, just that they are like in this joint state, this entangled state that if Wigner measures, he'll always get this outcome.
Yeah.
Fail, okay?
Yeah.
So then Alice's chain of reasoning is, okay, then if I start with, when I measured this first particle, I got 1.
Yeah.
I prepare this state,
Wigner must get...
Wigner must get fail.
Yeah, that's okay. That's the logic of the experiment, yeah.
Okay, so then we have A equals 1, Wigner equals fail from Alice's perspective.
Yeah.
What does Bob think? Now we go back to Bob's thinking. Just after he got S, if he tried to guess what's the outcome of
For Wigner.
For Wigner, yeah? He thinks, well, if I got 1, we'd seen before, then I know that Alice will get 1. And I know that Alice knows that when she gets 1, Wigner will get fail.
Yeah, it just feels like a circle, like sort of,
yeah. Or at this point, it's not a circle yet. It's kind of a chain of like, I got this. Starting to look like this meme. Okay.
Yeah.
Starting to look like this meme. Okay.
Are they communicating here, or is it
no,
just
they
them
don't need to
reasoning?
communicate, right? It's just reasoning, right?
Them reasoning about sort of what other agents will see.
Yeah, it's just reasoning about what our agents will see. And the part that you need to take my word for it is that, in this step, Wigner will always get fail if he sees this because that's quantum mechanics. Yeah, and the part that's also strange is that, Bob sees himself as classical, but for all this reasoning, he's taking into consideration how Alice thinks, and Alice sees him as a quantum system, right?
Sorry, again, how's that sort of the what?
I mean, we're doing this chain of reasoning across kind of different cuts of the different Heisenberg cuts for different agents. But this still goes perfectly. So far, okay?
Yeah. It's no paradox at this
There's
moment.
no paradox at this point. It's an experiment you can make with, a small quantum computer with quantum bits instead of observers, and you just run the circuit and you do a measurement here to see what did Alice get, what did Wigner get, and they're always, this is true.
Yeah.
Yeah? Good. The problem is that if I put another agent here, Ursula, and she does some measurement in Alice, then this whole thing will break down.
Okay.
Because, let me try first without going to the maths.
Yeah.
What they found out is that,
It's just funny because this is like a very long, complicated way
of
saying that stuff is still just very logical. If you apply the logic, you get the same results.
Just apply the logic,
We just made it very complicated with this quantum setup. But okay. But we need that. We need that because we want to understand why things break down if we add another observer. Okay, check.
So what will happen is that here, at some point, maybe before Wigner's measurement, Ursula will do the same. She will kind of undo Alice's measurement. She'll perform a big complicated measurement here, right? She'll get some outcome, which can be again okay or fail. Okay. And and then she'll reason the same way that if she gets by just looking at the whole quantum state, she can see that if I got okay, then Bob got 1.
Okay.
I'm not explaining you this, but it's something similar to this.
Yeah.
Right, so she sees Alice as being in this superposition. She knows all the things that happen until here. She thinks of Bob as like outside the cut because she wants to reason about his outcome. And just from the properties of the quantum state, she deduces that, okay, if I got this outcome,
Bob got
1. Okay?
Yeah.
So now if we chain the whole thing.
Yeah, because measuring Alice in his lab gives Ursula information about what Alice sent to Bob. So then she knows what Bob sort of got. Yeah.
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 In a way.
Yeah.
Yes. So if we chain the whole thing, what Ursula knows is that if she got okay, Bob got 1. She knows that Bob knows that if he got okay, that if he got 1, Alice got 1.
Yeah.
And she knows that Alice knows that if she got 1, Wigner got fail. So far, so good. It just looks like, okay, if Ursula gets okay, then
Wigner gets fail.
Wigner gets fail.
Yeah.
Now the problem is that if you just look at, now we look at it from the outside, we just look at this whole quantum circuit here. So we put our Heisenberg cut around the 2 labs. And just think, yeah, all these operations happen, and at the end we do these 2 measurements.
Yeah.
There is a probability that they're both okay.
Okay, whereas we just said when one measures okay, the other one is fail.
Yeah. So yes, that's
Okay,
that.
and you say 1/12 of the time.
Yes, it's just something you can deduce from the maths. You just look at this whole quantum state, you run this circuit, and then you do these measurements.
Crazy.
1/12 of the time.
Okay.
They'll both get okay.
Yeah.
The problem is like now when they both get okay, Wigner asks Ursula, so what did you get? And she's like, oh, I got okay. And Wigner goes, okay, so I know that you got okay. So Bob got 1, so Alice got 1, so I must have gotten fail. But look at my measurement outcome. I got okay.
So you, and then he would say you have to have seen fail. You have to have a fail because I have okay.
Right, but he's like, no, look here it is. I got okay.
And there's no, and none of them can then sort of say there's an error. They know. If we compare it to just nodes in a computer network, they know the system, the transistors, everything is just the algorithm is okay, the system is okay. It's just a paradox.
Right, at this point it'd be just a paradox, right? Everyone used very reasonable logic. So what is breaking down? So something.
What's breaking down here?
Yeah.
Logic, I'd say. Logic is breaking down.
So.
And also with accuracy, 1/12 of the times it will happen. That's sort of the mathematics tells you.
Mathematics, that's 1/12 of the time they'll get this result. Both get okay. And whenever this happens, then always they'll find a contradiction.
And you cannot sort of say when. So it's almost as if you have sort of, you know that you have an error. You can accurately say I have an error 1/12 of the times. Let's call it an error.
Yeah.
But you cannot predict when you get the error.
Correct.
You
yes.
don't know.
I mean, yes. Yeah. That's right. Yes. So.
Yeah.
So
when you get an error, you don't know who's wrong or right. I mean.
Right. This is a
Wigner
decision.
There's no. Or can we stand outside and say Ursula's right or Wigner's right? Or
you can say what you want, but this is still your choice, right? Something made you decide which one of them is right. Like maybe some philosophical principle that you have. Maybe you think, look, no, it's much more immediate that Wigner looks at here and says, okay, so this must be the right thing.
Yeah.
Whereas going through his chain of reasoning, something must be wrong with that.
Yeah.
Right? But again, this is a decision you make.
Yeah, and just for ours, we will share like the whole experiment and the papers and stuff. So we have the explanation here. We will share it.
Yeah.
I can hardly follow. I do follow because I've read the paper, but I'm of course, as I said earlier, I'm very much in it for the philosophy. So I'm just like puzzled here because we have a logic breakdown, a very quite profound paradox here. I always find it hard because I'm just not in that sense analytic enough. I know that how you present it is correct. So, and I follow sort of the steps. I just find it hard to keep it all together in my head.
Right.
So
maybe what I can tell is like each of these inferences, we saw how to do it. Like we saw this one we followed very well. Bob trying to guess Alice's outcome could be done classically.
Yeah.
It's a very logical little thing. Like this one and this one are a bit more complex and I cannot explain it without math. I just have to tell you like, yeah, look, Alice looks at the quantum state that she prepares, knows how it evolves when Bob entangles, and then knows that from here, Wigner will always get the same outcome, fail. Mm-hmm. So the same kind of reasoning is just a little bit more involved to explain without maths. And this is the same, right? So all the individual steps, this is just like applying basic logic and a little bit of quantum mechanics.
Yeah.
The problem comes when we start to combine them. And now, what are some ways out of this paradox? Okay.
Yeah.
So one is like the many worlds view. It's like, okay, maybe this is just an expression of many worlds view, where like, yes, Wigner sees one outcome, but he also sees the other outcome. Okay, so it's like saying, okay, maybe in your logic system, logicians can come up with whatever logic systems. It's just maths, right? You just put some axioms in, and the machinery gives you some things. And one of the axioms you can put is saying like, no, it's okay for Wigner to know that he gets an outcome and also that he gets the opposite outcome.
Yeah, to basically, I'm okay with facts that seem to be in contradiction, but I can account for that because I say it's many worlds interpretations. Yeah. We're on a different branch of the wave function right now, or something like that.
Something like that,
yeah.
Yes. The problem is then, okay, and now you try to apply that kind of logic as you go through the world and try to make decisions, and it's not a very useful tool, right? Because it's a logic where like, yeah, I can get hit by a car or I cannot get hit by a car. So I'll just cross the road. I don't know.
Yeah, it's not very operational.
It's not very operational, right?
No. Okay, so many worlds would say that's what's happening here, and then that's why it seems like a paradox. Yeah. Okay. So
there's many worlds. Yeah. There's more many worlds than there are many world believers. Yeah. So some people who believe in many worlds, and on some days might say that. So another way out of this is just saying, no, we're trying to combine all these statements.
Yeah.
But we're combining them kind of across different physical theories in practice. Case like, is it as if I was trying to combine, I don't know, we're analyzing some political situation, and there's a chain of people that need to give us insights, but each of them has such different approaches that at the end, like you get just like, I don't know, the things are incompatible.
Yeah, because they're applying different forms of reason or logic.
Yes, so it's not the logic they're applying that's different, but they're modeling the world differently. So Alice is modeling this and this as quantum systems, whereas Ursula is modeling all of Alice's lab, including Alice's memory, as a quantum system, right? And Bob is just modeling the two particles as quantum systems. So we're having agents with different Heisenberg cuts.
Yeah.
And clearly something goes wrong when we try to combine logic across these different Heisenberg cuts.
Yeah, and what interpretation of quantum mechanics says, we can expect these paradoxes to arise then if you model differently? Is that...
I mean, most of this kind of objective versions of Copenhagen interpretation. So neo-Copenhagen interpretations say the Heisenberg cut is a tool that we use to separate what we treat as quantum from what we treat as classical, but where you put this cut exactly, whether you include the protons inside or the photons that hit your eyes, like, it's kind of flexible. And agents can put it at different points. Right, so this would be one option. And then maybe a more objective Copenhagen thing would be like, no, there's limits on where we can put this thing. Maybe like, if you're in some kind of multi-agent system and there's people who consider each other agents, then no Heisenberg cut should include other agents as quantum systems, right? Otherwise the logic breaks down. Something like this. There's also, of course, collapse theories, which just tell you, no, you cannot put the Heisenberg cut around Alice because there's some objective collapse going here. The systems are too large. There's too much dissipation with some environment or some background field, whatever. And this is not this evolution. This gate is wrong.
Yeah.
Okay? And that's just saying, okay, quantum mechanics does not apply at this scale. No?
Yeah.
So most physicists at the moment, they think the way around this is by saying, no, there must be some compatibility conditions between Heisenberg cuts, some rules for when can I combine this reasoning, even if we model different systems as quantum or classical, and when can I not?
And if we know those rules, we won't get the paradox.
This would be the case. Then the solution would be like, in this case, this violates these rules, so you should not be allowed to change statements like this. Right? Okay, so now we have this extravagant thought experiment that will never be realized with people because this involves extremely complicated measurements, but which teaches something. It's teaching us that like the way we're using quantum mechanics is kind of breaking down at this level. Okay?
Yeah.
And an analogy to go back is like Maxwell's demon again. So Maxwell's demon is an experiment that again will not be made with a real demon and all the particles of a gas. And again, it shows, oh, look, thermodynamics is breaking down. So what solutions are there? And one solution was, okay, we need to bring the demon inside the theory. Another solution would be, no, we keep the demon abstract, but we take the perspective of the demon. And then from the perspective of the demon, it was work all along. We never had heat because they always had information, right? Mm-hmm. So now what can we do here? And this is related to kind of, this experiment can be formulated as a no-go theorem based on some assumptions, but the solutions are this. So one option is say, quantum mechanics does not apply at this scale. There's some objective collapse going on. This is not the right circuit.
Yeah, you cannot treat someone in a lab being in a superposition. Yeah.
Option 2 is saying, well, maybe it's okay that you can get to different conclusions from different paths, because many worlds I do see okay and fail.
Yeah.
Another thing is like what cubism says, like quantum theory is a theory that helps me reason and make predictions. I always take my perspective to do this in a kind of a radical way, which means I should not be considering the points of view of other people at all.
Yeah.
At least this is what cubism would have said 5-10 years ago.
Yeah.
Although things are evolving also within that interpretation. And finally, the other way out is just saying, no, we just cannot change these statements because we're combining different Heisenberg cuts. And we need to find some kind of rules for compatibility between Heisenberg cuts. Mm-hmm. Okay? And the problem there is that whenever we find these rules, either they are so strict that, okay, we don't find a paradox here, like, okay, I can always think of your analogy if you have exactly the same Heisenberg cut, but then there's many applications where this theory is useless, I can't make prediction. Or it's a bit more generous, like, okay, if our Heisenberg cuts don't exactly match, but they're a little bit, I can still think of you as an agent and do this reasoning. I know that you know X. And in those cases, in general, we can find a paradox. So we change the setting a little bit and we find a paradox. Right? So there's no kind of easy solution as of now.
They all come at a price, right?
They all come at a price, yes.
Yeah. And they all are so counterintuitive in how we experience the world.
Yes. It's the same idea as in Bell's theorem, right? You start with very intuitive assumptions.
Yeah.
And you find a contradiction, so you need to let go of one of them. And none are good. Yeah.
So we have different observers all reasoning quantum mechanically, and we are syncing them up, letting them communicate with each other.
Or let them thinking about each other's thoughts.
Yeah, but I mean, there's interactions. We have one preparing a particle, and then
that's the only
goes
thing,
in between, and then we end up with just different stories.
Yeah.
Different stories about what's really the case, or what is sort of
about what happened.
That's super weird, right? Yeah.
Yes, it's like they really experience different realities, right?
So we have thought experiments, physics that enter sort of the arena of metaphysics, that it doesn't tell us what sort of reality fundamentally is, but it does tell us that certain assumptions cannot be true at the same time, right? If you sort of apply that approach, so the no-go theorem approach and the metaphysical assumptions that are put to the test to this particular thought experiment, the FR thought experiment, what are sort of the assumptions underneath this experiment that cannot all be true at the same time?
Right. So there's many ways to formulate the assumptions. It's like you formulate a set of assumptions, and the experiment is kind of the proof that they cannot all go together.
Yeah.
Right. So in the original paper by Daniela Frauchiger and Renato Renner. So they had, I think, 3 assumptions. One is that quantum mechanics applies at these scales. So I'm not even saying like universally, but that I can put you in a box and model you as a quantum system. Like the agents could model each other as quantum systems.
Yeah.
I'll just go through the assumptions first.
Yeah,
right?
then we can go and I'll ask questions per assumption. Yeah, good thing.
The other thing is something about logic, but it's also, the way it's phrased, it's like a mix of logic and something about quantum physics. It's like, I cannot conclude one thing and its opposite. If I'm Wigner, I cannot conclude that I'll see the outcome okay, and also that I will definitely not see this outcome okay.
Yeah, just
right?
Not have that contradiction.
Not having this contradiction, right? It's something about logic. It's also about something about our experience of a measurement.
Yeah, which
right?
sounds super commonsensical.
Yeah. The other thing is consistency of the theory across different agents. And this in practice, what it means is really that I know that Ursula knows, that Bob knows, that Alice knows X, and I can chain these statements.
Yeah.
Right? Which is, again, how we go through life and how we make decisions in most settings. So the thing that's the assumption that is kind of hidden here among all of this is like this freedom that agents have to decide where they put the Heisenberg cut, decide where to which systems they model as quantum and which model as classical, and that these other assumptions work together with this, right? I can do these chains of reasoning across agents that have different Heisenberg cuts, but that's about it.
Yeah, okay, check. That's an extra nuance on top of this, which we can go into.
Yeah.
But first to check them off, right? So are these assumptions to me sound very commonsensical also for physicists prior to this thought experiment? So if I ask the question differently, was this sort of a bomb dropped in the foundations of physics, this thought experiment? It does seem to me like pretty new, right? Because saying that quantum theory is valid at sort of this scale, at least in what I read, I thought most physicists thinks it is. And that you cannot have these contradictions. Also, I think most physicists would say, yes, indeed. If I perform a measurement, I'll get a certain outcome, and I cannot have sort of contradictions there. Mm-hmm. And consistency of the theory when applied by different observers also seems like super commonsensical to all the science we do and how we regard all theories of nature. So we have 3 assumptions that are quite commonsensical, and now this thought experiment tells us they cannot all be true.
Right.
Within the community, there was response to this thought experiment, and you together with Renato Renner wrote a response on that, right? Responding on criticisms. Could you sort of just briefly touch upon how this thought experiment was critiqued and what your response was to it? Yeah,
so most of the critics try to put restrictions on when can we apply logic in quantum mechanics. And the very common one is like, no, you should not be allowed to apply logic. I should not be allowed to think about what you think if I know that later someone like Wigner will come and measure your lab and destroy this, right? Because in this example, problems start happening when you have like these 2 super observers measuring the 2 labs. Right? And there's a few problems with this kind of criticism. One is that you cannot predict the future, right? You can always change his experiment, put the agents far away, space out their measurements enough or bring them closer, such that, you can put this final destructive measurement by Wigner in the far future. Mm-hmm. And what they're saying is essentially like, I cannot make predictions now if I don't know whether someone will come and measure my brain or measure your brain in 500 years, right?
Yeah.
Something like this.
Yeah.
Which renders this restriction a bit useless. Because if I just describe you an experiment, setting like in the next hour, please make a prediction. And then you ask me, okay, but in 2 hours, will someone come and measure my lab? Like, it's a bit strange to think that this would have an influence, right? That then you can move players apart in a way that this will like start bringing like violate relativity in the sense that like some action from the future is now. And
so that criticism would also apply to a lot of other different theories,
Yes.
and then also so it's a bit
exactly.
of sort of I don't know how you call that in philosophy, but it's this sort of argument that sort of doesn't really. Well, then you have a lot of other problems if this
Then you have a
criticism
lot of
also-
other problems. Yes. The other thing is also like, where is the line? What is classified as a destructive measurement by Wigner? Because again, measurement is just an evolution. It's just a physical evolution, right? Of a particular type.
Yeah.
And maybe these experiments have a very specific, very dramatic kind of measurement type of evolution, where you see this terrible paradox. But there must be lots of intermediate cases where it does a measurement that's slightly different, or maybe it's a little bit more noisy, and still maybe you don't get like this contradiction, but you get some mismatch in probabilities of your predictions, right? You still get something that you wouldn't want. And it's very hard to put this line somewhere.
Mm-hmm.
Like, does my brain interacting with the environment and kind of dying, does this constitute a measurement? Would this be a measurement of this type? Like, can I not make predictions about whether the sun will die in a few millions of years just because of what will happen to my brain between now and then? All these things are not very practical. And to be maybe a bit more precise, there's lots of settings where we have partial information about how you model the world. Maybe in communication scenarios, like you send me a message and I try to guess something about you based on this message, for example. I should not need to know like exactly what's your view on the world, what do you model as a quantum system or whatnot. Like, if I need to know this for everything, if I need to keep track of all this context in a big chain, then again, the theory is not practical, right?
Yeah.
I pay a price in complexity.
Okay. Yeah. And so now I guess we're very deep into sort of technicalities, of course, because I asked you, so this is on me. I will put the paper in below in the description so people can read sort of the criticism and your response to it. I guess the reason why I asked is because I was just wondering if sort of the consensus of the physics community is that this thought experiment is indeed something we need to take quite serious. And I think it is, right? Because we were both in Vienna, where Renato and Daniela were sort of they were awarded sort of the Paul Ehrenfest Award for Best Paper in the Foundation of Quantum Physics for this paper, which to me signaled that, hey, the community is taking this quite serious, right?
Yeah, and there's other papers in like the one by Czeslaw Bruckner and the one by Eric, who were also there in Vienna at this interview, that have similar flavor, right?
Yeah, exactly.
Of being like, what we used to call facts, which are observations, are not absolute, and are in fact we can find these contradictions between observed facts between different people. So I think yes, there's quite a awareness in the community of this. It's still a very niche community within physics. Yeah. Yes.
And I mean, Eric Cavalcanti calls himself a metaphysical experimentalist. So he already sort of owns sort of the metaphysics as saying, okay, these experiments enter the arena of metaphysics. There's a tension, right? Because as physicists, you're not philosophers, but you guys are doing these thought experiments that do enter sort of metaphysics, because we are now talking about sort of just ground assumptions about reality. Is it sort of is there an objective reality the same for all observers? Or can we formulate theories that apply to this common shared reality? Stuff like that. And this thought experiment places us, sort of confronts us that we cannot hold all these assumptions to be true. So then what guidelines do you have as a physicist, or how to navigate these assumptions then? Is it just a matter of preference to say, I will let go of sort of the consistency, or I want to let go that quantum theory doesn't apply at all these scales? How do you navigate that?
A tough question.
Sorry, I know.
So first of all, like, I agree with what you said. This is like physics entering philosophy, and also that as physicists we are very unprepared for this. Like, you do a whole degree in physics without having a single philosophy class or metaphysics or anything, and sometimes it would help just being a bit familiar with the kind of concepts that are treated there. Yeah, so how do you navigate these things? So some of these assumptions can be tested, right? Like quantum mechanics applies at this scales. We can test it. It's like testing collapse theories, essentially, right?
Yeah.
Larger and larger superposition. So that's kind of
the
put to rest for now.
Yeah, experimentalists are working on that, right? Seeing how to. Do you know where are we now? Is it sort of at the molecular level?
I think yes, small molecules. I mean.
Yeah. Okay, so we can keep on doing that just test. Can we get to the level of an observer in a superposition?
Yeah. Exactly. Okay, check. Yes. The other ones of putting limitations on logic. Again, this is something we can test to some extent because we can say, okay, I'll try this limitation. Say, I cannot think about your thoughts if we have incompatible Heisenberg cuts for some definition of incompatibility. I want to test this definition of what compatibility is. And then I can test this and see like how far I can go or not with this, right?
Yeah.
And see, okay.
And sorry, just to be clear, when we talk about sort of these differences in Heisenberg cuts, it's sort of disagreement on where we put the boundary between quantum and classical,
exactly,
right?
Exactly.
So and so we can't say, okay, I'm not sort of. We have to have a sort of an agreement on where the cut is between classical and quantum. Yeah. Because
if we do, then we don't have this kind of paradoxes arising, like this specific kind of paradoxes. Of course, you still have contextuality and whatnot, but but not this kind. Right? So this is one of the reasons. Maybe it's a good time to do a segue of why we wrote this paper with Renato and Mathis and Nurgalieva on. Called thought experiments in a quantum computer. So the idea is there is to like model a little program that can be run on a small quantum computer like the circuit I showed, where you need to program all the assumptions that you put in.
Mm-hmm.
So you need to program how you model each agent as a quantum system, where they put the Heisenberg cut, what kind of logic they use, what interpretation of quantum theory they use, and then you can test this and see if you find a contradiction or not. Right, so this is kind of our way of trying to navigate, like to answer your question, to navigate. How do you cope with this?
Yeah, that software is called Quanundrum, right? You're working on it. Is it sort of working yet?
I mean, there's like a prototype version that is on GitHub. If people can download.
We'll put it down. Can we put it down in the description?
You can. I mean, it's not amazing. I mean, it was programmed mostly by a very good master student we had at the time, Mathis, and then we Nuriya, and maybe a little bit I refined it a little bit.
But I mean, it's coding this, right?
It's coding this.
Yeah. And then so we now have like thought experiment software sort of to run these
essentially, yes. And then it spits out whether it tells you what were the predictions of all the agents and if there's a contradiction or not, right? And then you can say, okay, now I want to add one more agent, or I want to change the protocol of what they measure.
This is cool stuff because it's basically sort of metaphysics software, because we now have, you can put in assumptions and play around with it and you get contradictions and stuff. So this is really where physics and philosophy meets, right?
This is cool, yes.
Yeah. And are there sort of already preliminary findings coming out of Quanundrum or working on this that lead you to say, okay, I put my bets on letting go this assumption, or I think we should keep this assumption about reality? What are your sort of thoughts there?
No, I mean, the results are kind of what we expected, because also what we tested is the things that we were more familiar with, right? So ideally we would have lots of people playing with this and telling us their insights and improving the software. But, of course we see, if you have a collapse theory, then you don't have any problem. You don't have any contradiction. Of course, collapse theories have other problems outside this program, right?
Yeah.
It also shows, yes, if you have many worlds, then again, you don't have. If you program the agents to believe in many worlds, then there's no contradiction in the results.
Then you can let go of that one, because in a many worlds scenario, as we said, sort of the fill and if both have an okay where they should contradict, or we have a contradiction where they should agree, in a many worlds interpretation, that can go because you're just on different
That's it. Branches, and there's also like that Alice, when she does the first measurement, she thinks of herself like, oh yeah, I see this measurement outcome, but I am in a superposition of seeing this and that.
Yeah.
And now I keep track of this.
Yeah.
Which is a fair enough assumption. And again, the price you pay here, and this is very clear also when you program it, is complexity. It's like, imagine every time you see something, you need to keep track that, oh, I'm seeing this, but I'm actually a superposition of seeing this and that and that
exactly.
and that and that.
And talking about sort of these quantum classical divide and that the Heisenberg cut. So we have objective collapse, which says we will find sort of this objective point where to put the cut, and that's the same for all observers, right? And we have many worlds say there is no cut. Basically, right? Because the wave function just branches off, and there's not this quantum classical divide. And then we have like these epistemic approaches that do say it's really up to the observer to put the cut. Is that a way to say
depending on the epistemic approach you have.
Yeah.
I mean, many worlds also says that many worlds does not deny that you have a subjective experience of seeing one thing, but it says. Yeah,
and
it's
just
an
for
illusion,
people to,
right?
again, I guess, good to just sort of epistemic approaches. What are we talking about? Sort of epistemic interpretations of quantum theory.
Yeah, this is like quantum theory is about our knowledge.
Yeah.
Maybe one of the most radical examples is cubism, where like quantum theory is like a tool that I use to navigate this world that helps me make predictions, to win bets about the like outcome measurements. Of something.
It doesn't tell me what I'm measuring, and it doesn't tell me what measurement I will get. It's just me betting in the universe of
which is fair enough, right?
Yeah.
We cannot really say more than that. But the problem is that, it's a relatively recent theory. I don't think it had been like really confronted before this kind of experiments with, it's not just about my knowledge, but now how do I combine this? I need to take into account the point of view of other people.
Yeah.
Right. So for this, it has a problem here. If you just wanted to apply like the vanilla version of this theory, it would be, Wigner only can reason from his point of view. He should not be allowed to like take this thing lying around like Alice and treat her as another agent and think of her as an agent and reason through her.
Yeah.
Right? Which again, fair enough, then you don't get a contradiction. But then there's also lots of other experiments you cannot do. Like, I don't know, if you're trying to predict the behavior of someone based on the result of some quantum measurement.
Yeah.
Then like cubism would not be the right tool to do this. Yeah.
So cubism has a hard time to sort of restore a common shared reality in a sense. So it does give you a way to explain these contradictions, because it say that just different observers using the theory.
Yeah, and you don't combine them. You just don't combine them.
Yeah, just don't combine them. You have your own truth. But if we want to sort of restore sort of a common reality, it has a difficulty.
And also like you don't go very far if.
But what puzzles me a bit, Lydia, is that when we sat down in Vienna with Renato, he only later I read that in this Quanta magazine article that he initially thought that this thought experiment was sort of favoring many worlds. Let's say, okay, to account for this weird paradox, this seems to be most compatible or with a many worlds interpretation. And then later on, when I interviewed him in Vienna, when you were present there, right, he was pretty outspoken on the fact that he said, no, I really think these epistemic approaches and interpretations are the way forward. And not in a cubist sense, perhaps, but still. So I found it really very interesting. Have you had discussions with him on this, or what do you think?
A little bit over the years, but again, our opinions change.
Yeah, maybe. But what are your thoughts? So would you say? Can we even say that it doesn't favor anything because it just tells us what we cannot be true at the same time, but still sort of...
Correct. I mean, it's not even about what cannot be true. I don't think quantum mechanics as a theory, as a tool, like in the same way that thermodynamics is a tool to help us build trains.
Yeah.
Quantum mechanics is a tool to help us, make predictions about a thing going on that we can witness. But in that sense, I'm more in the epistemic thing. But I also think that, every theory, it's like this Gödel incompleteness theorems. Every theory, at some point, if you find like a self-referential problem, you'll get to a paradox. Right? This also happens. There's some funny examples that I don't remember in classical mechanics, where you find this paradox and then the solution turns out to be like a quantum phenomena. But like even every logical system, you make something that's kind of self-referential, and you find, and it's a paradox. It's just a limitation on logic.
Does it?
And this is, in a way, it is, right? Because it's kind of quantum mechanics describing itself. Like the observer through this long chain is kind of describing itself as a quantum system, and that's where
Who wrote that paper again? Sort of quantum mechanics cannot sort of describe. Is this also Renato, or
this is the title of the original paper by Renato and Daniela?
Yeah, exactly. Cannot consistently describe how to use itself. So it's just this Gödel incompleteness thing. So it points in the end to the incompleteness of quantum mechanics, then, perhaps.
Yeah, which is not surprising, right? Because any theory is incomplete in this way. Any theory that tries to be universal has to be incomplete. So Nuriya Nurgalieva, my co-author, her PhD thesis is exactly on this and comparing this to other types of paradoxes. Like even like the simplest example is this sentence is false. Right? If you try to assign a truth value to this sentence, then if it's true, then it's false. If it's false, then it's true. You cannot do this. And this is like a more complicated example of this, where you needed a lot of technicalities to kind of reach the same conclusion.
Funny,
right?
In the answer of this, just say this sentence is false.
Yeah.
But but I did why I did think that quantum mechanics, because also a bit sort of physics history, but I mean, Einstein said the theory is not complete, and he came up with a way why he thought so, the sort of the EPR paper, and then we had John Stuart Bell putting it to the test, and he did not prove it is complete, but he definitely did prove that it is not incomplete in the way Einstein thought it was incomplete, because Einstein thought of these local hidden variables, right? That we but those are ruled out. So I thought that physics was very much sort of on the page that quantum theory is sort of our most complete theory of reality.
I mean, we know it has some problems at some levels, like when it enters in conflict with general relativity.
Yeah.
We're only just, I mean, it's relatively recent, the field of studying what is a reference frame in quantum mechanics. So when you say spin is up relative to what? Right? It means that like, we have something else that we use as a big magnet that this defines direction up. This big magnet is also a quantum system. What happens now if we play with this?
Yeah.
And so I think there's still a lot to explore in quantum mechanics. There are many no-go theorems for incompleteness in the sense that you meant, like ruling out many classes of hidden variables. This exists more and more. Of course, all of these theorems bring in other assumptions with them. Yeah, but this is a different type of incompleteness. So it's like the Gödel type of incompleteness. Like we can find sentences within this theory that cannot be proven true or false. That's it. I mean, does it bring problems to us? I guess this is more like, does it have practical applications that could be problematic already, right? And this is something that people are starting to explore now. So can we take this kind of no-go theorems and now find a practical scenario? Maybe like instead of 4 observers, you have 4 little quantum computers. And if they reach these contradictory conclusions, like, can this result in problems? Like, can we find a game such that then this really results in problems? Can we find a scenario where this is...
We don't know yet.
I think this is still active research, yes.
Yeah, but it might. And that's where I think as a storyteller or sort of science fiction mind, I do think that's very, very interesting, because if it does, if this would apply, so we could see this, then we would need 4 quantum computers or 2. Just Alice and Bob in their box would be a quantum computer.
This would be an example. Yes, you can also think of Ursula and Wigner, the quantum computers, and Alice and Bob are like sub parts of this quantum computers,
check. Like
measuring a little quantum memory that.
Yeah.
And
but then we would have like a node of 2 quantum computers in the future that we use for stuff, and then in 1/12 of the cases, sort of the logic breaks down.
Something like this, yes. But again, it's a fun project for someone to take in. It's also very broad project of like, okay, not try to find a problem with this,
But I mean, it is sort of the work, because now it might be still science fiction, but thinking about the work of John Stuart Bell, which at that time was also thought of as just sort of philosophical or metaphysical, but then it led to quantum information and the quantum computer, right? So why wouldn't this lead, for instance, to a breakthrough technology, or perhaps like a big fundamental problem in quantum computing,
right?
When we combine quantum computers.
Yeah, this is why we need more funding for fundamental research. So for example, Bell's tests have lots of applications in cryptography, where you want to, because like this lack of hidden variables, like this lack of like nobody could have predicted what this things could be, also tell you that it's a way for 2 players to create something truly random between them that they can test, that no adversary can check, right? So it can be used in cryptography. And here we don't know. So the answer is that we simply don't know. It makes me worried a little bit that if you try to imbue logic in quantum computers, that maybe we'll reach some kind of problem like this, and it would be a cool project to investigate how. Yes,
it seems pretty. It's cool, and it's eerie in a sense that it breaks down, and that it would be sort of a huge anomaly, I think, in just the whole paradigm of computation if it does break down.
Right.
Yeah. In Vienna, when we talked about it with Renato, Czaslaw, and Eric in a previous video, they all said this is like crazy for us too, because it was sort of an extra layer of weirdness, of craziness, in addition to Bell's theorem that already tells us that we cannot have sort of local realism and sort of freedom of experiment, that we cannot hold these assumptions true at the same time. So what is the addition here that makes it extra weird?
So the thing that it adds is like, oh, look, if like Bell's theorem does not disprove observations are facts and facts are universal, you can tell of this in Bell's theorem. Like you have these 2 agents far away, they measure their spins. True, universal. Like the spins are now spin out. It's a fact of the world, right?
Yeah, it might not be local, but then it's a fact of the world.
And I mean, and one way to check is then go and ask them.
Yeah.
Right. And what this experiment tells is like, no, there's no common experience of reality. Okay, I don't think facts of the world is a very useful expression, because we only have our observations to go by.
Yeah.
So like, even if I say like, okay, forget about facts of the world, but our observations are consistent, right?
Yeah.
I look at this apple and it's red, and you also see it being red, right?
Yeah.
And this is like we can find situations where like we really have a radically incompatible observation of reality. Even when we're using the same physical theory, okay, we're applying it to different domains, but like the facts are really incompatible. Right? Like Alice really predicted 100% probability that you'll measure fail, and you measured okay.
Yeah.
Right? So this is the extra layer of strangeness. If you're very attached to, there must be a common reality that we are, like, science is a way to get to this common reality, right?
Yeah.
But one way to look at it is like, we only get to this common reality by kind of talking to each other, by correlations, by diffusing through the environment.
By performing measurements and talking.
By performing measurements, by having like the molecules of air escaping your lab and coming here, right? Correlations is what gives us a common reality. This is currently the way I like to
And would you
Look at it.
agree that just sort of this is sort of more on a sort of philosophy note that a common physical reality, we're talking about physical properties that are common, because there could be something underneath it all that still is very objective, observer independent, but it's just not sort of physical or...
Right, so there could be something underneath it all, right?
Yeah.
So you can model everyone in this experiment as a quantum system and have like the global Schrödinger equation evolving this whole thing, right? So yeah, sure, we don't deny this, but this is not useful to us, right? Knowing God's view
that's
of
like
the universe evolving.
Purely metaphysics there. But
it's not just this, like it doesn't tell us anything about our experiences. You cannot have both like this outside view and know what people are experiencing inside the experiment, right? If you want to have this, if I want to reason with the things I see in the lab or with the things I see around me, I look at you like photons hitting my eyes, quantum, this is a quantum process, right? If I want to reason with this, then I need to necessarily take an Heisenberg cut somewhere, right? Take my perspective.
Yeah.
Right?
Bernardo would say I have to dissociate, or sort of there has to be a dissociation. It seems like it's another way philosophically to talk about sort of a cut between two personalities. This is fascinating because I remember when we had a pre-discussion of this conversation and talking about what it all means, you had this metaphor of this God's eye view. Like I can give you Super Mario on a disc, here's the game, and then there you have it. That's the universe. But we both know that the game is to be played and to be in it and to have these different perspectives, and that's the experience of the game.
Yes,
is that's what you're hitting at here, right?
Yes, It's also one criticism that many of the shut up and calculate kind of physicists say of this is like, you should not be allowed to take the point of view of these little agents inside their boxes. Like, just apply the Schrödinger equation from the outside. You see everything evolving, like, beautiful.
Yeah.
but we are the little people inside the boxes.
Yeah, exactly. And that doesn't tell us anything in the end.
Like, we are not experiencing the video game from the perspective of the developer outside reading the code. We are inside the game.
Yeah.
Right?
This is so interesting. Yeah, And also, I mean, the outside view then, how do you say that? It's not computationally reducible in a sense. You cannot sort of, it has to be played out, right? It has to sort of render itself out. You cannot, I had a conversation with a complexity scientist, James Gladfelder, about sort of information and the game of life, that Conway game of life with simple rules. You get to sort of very complex, you get to like avatar and whole worlds, and you just started out with this simple grid with just super simple rules. But I think sort of the philosophical takeaway from Conway's game of life is that there's no way where you can get from the initial state to that sort of end complexity that the game will give you if you just render it out. You have to go through that. You have to go through the computations. You could maybe speed that up with a supercomputer, but there's no way. But I might be misunderstanding this. There's no way algorithmically to sort of
to
know
predict
from
what
state.
goes from.
Exactly, you have to go through it, right?
Yeah, so I don't know about this particular example, but I think there's many examples of computational problems that have this property it's already maximally efficient. You cannot predict without kind of iterating it. Yes. Yeah. And the same can be true.
Yeah. But so you basically said you are not sort of, you say, okay, I'm not a philosopher, and we are, as physicists, perhaps a little bit unequipped we don't have the right tools to strongly distinguish between these assumptions, which one is the most plausible. But hearing you talk, it does, so you do seem to favor more of these epistemic interpretations. So, or
I
are
guess
you just...
so. So I think all theories are, because of the way we are built, because of the way we interact with the world, all theories are about our interactions. Yeah. Right? Even whenever we talk about causality, cause and effect, like even in astronomy, say, when I say, there's this gravitational law and this is why the planets move around this, it's not like I'm going around and like changing the planet unless I'm running a simulation, which can be done. But we do think about it like, oh, what would happen if this planet wasn't here, right? Which is a kind of intervention. We might not be doing it in person, but it's still about our relation, like what we could do. So I think this applies to, I now think that this applies to physics in general, but also like to other physical theories. So in that sense, yes, everything is about our knowledge. From our perspective.
And how would it be different if, say, the objective collapse is true and not this epistemic approach, that it is an objective theory about an objective world out there, or the many worlds is true, that we are just on different branches of the wave function and there is no collapse and it's basically all present.
Okay, if the objective collapse is true, that's easier.
Yeah, check. What would that mean?
Okay, then you'd not get a paradox in this situation, right? So there's something we can test eventually, like as we superpose large and larger systems.
Yeah.
And then we can, okay, well, at what scale does this objective collapse happen? Is it like 5 kilograms? Okay, so then can a small cat be an observer? Okay, or like I miniaturize you, and now you don't suffer this objective collapse, and I run the experiment, I still have the same problem, right?
Yeah.
Or it could be, I don't know, a collapse in consciousness and whatever when you do a measurement. Then fine, like, then okay, you don't have this specific problem. You still have many other questions to answer about your physics and how it interacts with the other branches of physics.
Yeah, what's the biggest one then? Sorry, I guess you just mentioned. But...
So with collapse, it has some problems with relativity, being consistent with relativity at some scale, for example. And also needs to justify where is this collapse coming from, like why is quantum mechanics breaking down at some scale?
Yeah.
Yes, but still I think that eventually we would find, in whatever physical theory, I think we'd find a paradox like this. So if many worlds was true, then I think again, like, fine, what does this tell us? What you're going to do with this information? Because I still need to use quantum theory from my perspective of seeing this outcome. If I need to keep track of all the branches of the wave function, it's not practical. Like, I cannot do this with finite resources. I'll very quickly run out of memory. So, okay, yes, many worlds is true. Everything that's possible to happen happens. Like, so much. Like, also, what a boring world it is. A world where everything happens.
It only wouldn't be boring if I could switch those branches, but that's unfortunately not. That's not how it works, right?
I feel sometimes I just have like fantasies of divorced dads.
What, of divorced
dads? So like people who regret their choices and like, okay, so what if live with your bad decisions? It's okay, we all do it. No, I have a friend who's a physicist called Johann Berg.
Yeah.
Who says that a world where everything happens is as boring as a world where nothing happens. So
that's one to think about. Yeah.
No reversibility. No consequences. It's
yeah. Which makes me, this is sort of really segue, but free will, do you sort of have in your, do you believe in free will?
I believe in relative free will. In the sense like, you cannot predict my actions. What is the source of free will? I mean, is everything I'm made of? If someone knew everything I'm made of, which, there's many arguments of, the complexity of this is would burn through every hard drive. You just can't do it. But then they would be able to predict what I do. But does this take away from my experience of thinking I have free will? Like, I don't know, we were offline, we were talking about children, right?
Yeah.
And like, when they're hungry, you can 100% determine that they'll be cranky.
Yeah.
But they still have their subjective experience of, like, no, it's my...
No, I'm reasonable. I'm being reasonable. Yeah.
And let them have this experience, right?
Yeah.
So I'm kind of at peace with like, okay,
Yeah.
if there's a super observer who can predict everything I'm going to do, like, it's okay.
Yeah. It's funny. It's almost as if sort of physics is now sort of confirming this sort of cliche, commonly held thing where people say every person has their own reality, right? And that's somehow and we all know that's not true. There are sort of objective facts in the world. So I'm a bit puzzled here because we still live in a macroscopic world where it just seems to be a commonly shared world that stays the same, but is observer independent. Is that just because we're then just completely entangled? Is that the way to put it?
That's I mean, this experiment was it's kind of very fine-tuned, very designed to reach this outcome, like to find this contradiction. But yeah, I think most of it's also it's what allows us to have a shared experience of time passing, is that we share systems like the earth, the sun, the thing that we use as clocks in practice. It's like everything that gives us a shared experience of a shared reality that we construct together, it's correlations. We need these tools to construct it, but that doesn't mean that it's really there outside of us or independent of us. I mean, personally I believe that there is a world that I'm not like in a box creating.
You're not
I'm not that smart.
You're not a solipsist. Philosophers call a solipsist. No, check.
But like all we can access is our experience of the world, like what Renato says, of like we're seeing this stuff through a screen, and we're interacting with the world through a screen. And what gives us like this idea of like, oh, we're interacting with the same thing is really this correlations between us.
Check. And so in your work as a physicist, you are at peace with the fact that your work is very much about how that screen works, how that interacts, and not so much about what it really points to, or what that really is, which is still metaphysics in the end.
I guess.
Whereas
I don't know, because some other things I do in my work is like thinking, okay, what if instead of living in a quantum mechanical universe, we lived in a stranger universe or in a simpler universe? So there's different physical theories that you can make up. And now see, okay, how would agents experience the world there? How would this be different? And this maybe gives us some clue of like, That's
interesting though, because I'd say, okay, we know we live in a quantum mechanical world, right? We have established that experimentally, at least microscopically.
As far as we can tell, it's a very good theory, yes.
And that world is pretty weird, but still also commonsensical. How would it be? What would a weirder world look like? What would a simpler world look like if you just said you think about that? So I'm curious here.
So I think we'll touch this in some of the other interviews. What I mean by a weirder world is like one with correlations stronger than quantum entanglement, for example. Where, you remember we talked about Bell's theorem, how it can be formulated as a game, where like classically you can only win it with like 3/4 probability. And like with a quantum strategy, you can win it like 80-something%. And you could imagine like, oh, what would be like a black box view of a world that would make you always win this game? Like correlations, like non-locality even stronger than what we have in quantum theory, right? And turns out like that this kind of worlds, if you impose this condition, like, okay, it needs to be stranger than quantum in this very specific thing, then it restricts like the dynamics of this. Just these correlations restrict like the dynamics of systems, like the physics of what kind of physics are possible there. And then it also restricts how we model agents, and if you find these paradoxes and so on. So this is one direction. I'm
super curious there, because do you have any clue how that would be for an observer in such a weirder world experientially? I mean, this is science fiction, of course, but
it is science fiction. But we looked into this. So there's a paper with Nuriya and Villasine, where we looked precisely at this world. And so one thing that is not stable there is the notion of a system, of like, I treat this thing as a system, as an observer, but then later on I need to kind of combine it with something else, and now this whole thing is an observer. So it's cool. Things that we take for granted in quantum mechanics, like, I call this a system, right? Which is, again, it's a choice. It's a choice of boundary that I do. Like this choice is not kind of stable in other theories.
It's fluid, and it's fluid.
It's fluid, yes.
Yeah. Would that also mean, because observers are systems in the end, that sort of observerhood is also fluid then?
Yeah, in a way. It's funny.
So your boundary between you and is just more fluid.
And so in that kind of world, you can still find this kind of paradoxes. And then we studied also simpler worlds. So like this kind of hidden variable worlds that simulate some of the properties of quantum mechanics, but they are classical. Well, it's like, all particles have a definite position and momentum. We just don't know. There's just like enforced ignorance. This is, for example, Speck and Stoy theory. In that model, what would it be like to be an agent in such a world? And then what we find is that it's very hard to then make decisions for agents to like take information and then depending on this information, making some decision and taking some action. This is extremely, extremely hard.
Why exactly? Why is it hard?
It could have to do with the mechanics of this particular world where like it's kind of all probabilities are 50-50 to some extent. So everything needs to be like, you cannot kind of bias your decisions more one way or another. It would be like
a very black and white world.
Yeah, it's a very black and white world. And then you don't find this paradoxes because it's a classical theory, so you're not expecting it. But also you're very limited what you'd be as an agent. So you can play around with these things.
This is just really cool because this is of course very technical how you construct these worlds, but it's just you can do this. So how do you do that? Is this all math?
So other people have studied. It's a very fruitful, I think, field of research to try to understand why is the world quantum mechanical. What we do is we test alternatives. Right?
Okay.
There's different ways to test alternatives. One very popular one is like, okay, treat everything as black boxes. Like maybe there's some electrons in a box and I shoot some lasers, but I just think of like, oh, there's some buttons I push, I get some outcomes. Mm-hmm. I study the probabilities, the frequencies of these things.
Yeah.
And now if you put quantum systems inside this gives you some probabilities. If you put a classical system inside this, you get different probabilities, right? But then you can like forget what's inside and just say, okay, what if now I want to see if I get different types of probabilities? So I fix the outcomes, and then I try to kind of reverse engineer what's inside the box. So this is a big field of research, called generalized probability theories that people. It's a way to study. It's like one direction to study how the world could be different from quantum theory.
And what will what's the sort of the this is maybe sort of not meant as an insult, but what's the relevance of coming up with these different worlds for physics? Where does it become relevant for sort of the foundations of physics?
So many things. So one would be that maybe we find something that is very close to quantum theory, right? Where the probabilities are like almost indistinguishable from what we can see, but which has much more intuitive properties, right? And then this would be, interesting. Maybe we should study this thing instead, right? Or maybe we try to find, or maybe this leads us to try to find an experiment to determine, are we in the quantum mechanical world or are we in this other world, right? Another direction of research people do is quantum theory is such an elegant theory, right? But it's derived from 4 or 5 axioms that are all mathematical. States are vectors in a Hilbert space, a measurement is... And it's not very satisfying, right? Because it doesn't tell us much about the nature. So there's ways of... directions of research where you just try to find more intuitive axioms that maybe they're more physical. And then from here, try to derive quantum mechanics. And then you can say, what happens if I change this a little bit? Yeah. Now I get a different class of theories. Why are we not there? Why is the world like this? So this is kind of the...
Yeah, I think this is all just very inspiring sort of as a storyteller and giving ideas for science fiction, right? We know the science fiction around sort of more many worlds kind of theories, that you have these alternative world lines, but then you end up in pretty much the same world as we know, but just different, that I can have like a different life, and it's all possible at the same time, and can maybe switch those. But it seems to me that the stuff you're working on could lead to even more exotic sort of science fiction. Do you have any ideas here?
Yeah, I think it's a very good question. I think quantum theory has the potential to inspire even more interesting science fiction. This is one of the examples. I don't know. In a non-science fiction thing, I've seen someone almost try to justify an affair with things like, oh, if they don't know, then
that's how you physicist, how you use this theory.
Like, come on, you cannot control correlations. It's not this, right? But yeah, no, there's very rich terrain here for stories that are exactly this, right? So we had alternative realities or experience of realities until we meet, and then what happens? Like, do we forget our previous experience, or do we? Yeah. I think it's something cool to explore that also has not been very explored. I have a friend who's a physicist, Nicole Junger-Halpern. Every year, she did it once. I think she'll do it again. She runs a contest of like short stories inspired by quantum theory.
Cool.
So like to give us
we
something
need to
like
go in those. Yeah.
Yes. So. I don't know, but I think there's potential here.
And because I think many people, of course, at the Essentia Foundation, we're about sort of analytic idealism, consciousness being fundamental, and idealism is associated mostly worldwide with people who are religious or spiritual, right? That's sort of the idealism we know that is sort of just ancient, coming from all these traditions, and we approach it analytically, and that limits what we can or cannot say. So if you ask me or Renato, or does God exist, I'll say yes, but not in the way you commonly think about God as delivered in these ancient texts and stuff. So you have all these limits because you want to approach it analytically, right? But I do think that quantum mechanics, for instance, inspires especially people who have this inclination, who are sort of spiritual, to say, see, everything's about consciousness. I can sort of just manifest my own world if I truly believe in things. And you have this sort of like this whole scene of manifestation. And they all sort of run away with quantum theory. And then, of course, physicists are annoyed by that. We even had this movie, What the Bleep Do We Know, like, which really popularized quantum mechanics. I think it's 20 or 25 years ago, but it just went off the rails because it had these fragments in it basically saying that if you want a Ferrari and just focus on it, you manifest, stuff like that. Yeah. But what's sort of the way how all of this informs you, or do you think how it can inform people on a meaning level? Can physics tell us anything there?
Yes, I think it's told me some things. One thing is that we draw these boundaries around us. We try to classify the world because that's how humans survive. Like, we find patterns and we classify things. Like, from this point on, it counts as a mammal. Before it doesn't, right? But nature doesn't care about these boundaries, right? Like the Heisenberg cut. I treat these photons as quantum mechanical, but not the ones that are entering my eyes. Yeah. Like this idea of like, be aware that whenever you try to classify something, whenever you try to draw a boundary, that someone else might be drawing it differently, and that these things are not. So one example, for example, when I teach the double slit experiment, I'm like, oh, is light a particle? Is it a wave? Now, because I have quite a young generation of students now, I say, look, this is like people saying that you have to be a man or a woman. Like, we created these categories based on some biology, but they're not always useful. Nature is more diverse than this. We said, we divide the world into particles and waves, but light is something else that has properties of both, right? So I think physics has really informed me in this. Maybe I had this inclination already, right? I mean, I'm biased too. And that's why this is the lesson I see in physics. Yeah. But yes, the main thing is really for me, it's more and more things are subjective and relational. You see a mess, I see my organized chaos, I know exactly where I put this thing. And that this I think it has helped me going through life. Yes, there's no universal bad thing. Like from the perspective of the bad person, they actually have, their own interests and views and stuff. And like this, helps me connect to people.
That's like this
intuitive.
non-dualist notion coming from physics here, that you say, okay, there's no objective way. To me, sort of it's funny because, I was brought up religious, and in religion, in Christianity, I was brought up was quite dualistic in a sense. Mm-hmm. Definitely when it comes to good and evil, and making that like very, very objective, right? Like God and Satan, and it's like pretty clear divide, and it's transcendent evil and stuff like that. And I still, when I'm entering into discussions with friends who are still more on that page, no, there's like pure evil, I'm much more like, no, it's us sort of having to think and navigate this. We create this moral landscape as mammals, as humans, and that doesn't make it's absolutely real for us.
Yes.
And right, but in the end, if physics also teaches us that there's no outside way to just objectively say this is the case for everyone, I can map that perfectly well with sort of a non-dualist way of looking also ethically at the world. Mm-hmm.
Yes, yes. Which is not like a free-for-all, right? It's not like all the options are true. Like, we have correlations. There's a reason why we consider some things to be bad as a decision that we make together, right?
Yeah.
It's not like, genocide is okay. It's not this.
No.
Right?
That's
just
not absolutely not. No. So, and were you brought up religious, if I may ask?
So no, not my parents. I mean, I was brought up in a Catholic country, but Portugal in, I think, still recent. I can still call it recent years. but my parents are not religious, but they're very artistic and culturally inclined people. But like, I went through a very religious phase when I was 6, 7, 8 years old.
Oh, that's interesting.
I was very.
That's pretty. You were devout then. Yeah.
Yeah, I was like comparing different versions of the Bible. And
Wow.
But then at some point, it's like, this is not. There's all these inconsistencies. It's not just inconsistencies. It's like, it's a very limited way of look at the world. And you look at different religions and learn a little bit from everything. And, a few points. One, I think it's very useful for scientists working on foundations. I mean, for everyone in general, but for scientists working on foundations to be aware of their own relationship with faith, religion, and their own mortality, because these things kind of sneak up into your research. And it's good to be aware of this. Of like, I don't know, I'm really afraid of death. I don't want to think about it. And then now suddenly I believe in many worlds in which, there's always a branch of quantum theory.
Are you
not
really?
me.
No, I know. Okay, but you really think that sort of these psychological mechanisms slip into even?
I think they do a little bit. That I favor some view of the world because of the way. Why was Einstein so upset about quantum mechanics? I mean, I don't think it's about his view with mortality, but about some way you're brought up and you think about how the world should work that you might not be aware of. And in foundations, I see many people believing something because they want it to be true, and then if you dig in enough, like sometimes they're afraid to die. And this maybe explains a bit of the generational.
Yeah, that's super. It's super interesting. I think it's just being brutally honest with how the human mind. If we say modeling the agent in any system, we have to also model in metaphysical assumptions or sort of psychological mechanisms that just play into how you want the world to be.
Yeah,
but then in the end, we do have to still this stick that can ground us, which we call mathematics then, right? Or still...
Yeah, I mean, of course, yes.
Okay.
Yeah. But it's about like, you have a no-go theorem now, which assumptions do you prefer, or which ones are you happy to let go of, or which directions do you explore from there? Sometimes like all these beliefs we have kind of
how does it... But how, if I may ask, how does it play into your view on your being a human and your mortality? Does your work in some sense sort of inform you about this? Is that
actually
yeah
Yeah, I mean, this was at university that I learned about what are waves. Like, think of a Mexican wave in a football stadium. Like, people get up and do this, and then the wave propagates, right? The matter moves locally, but the wave is actually propagating.
Oh, yeah, that's nice, yeah.
It's like, this is the perfect metaphor for life and death. I'm happy, I'm not going anywhere else. It's like, okay, I'm here, I do my own thing, I move a little bit, and then I die. And I'm part of the big wave, and like the wave propagates. And this doesn't mean like my spirit goes somewhere, but like my actions have consequences in the world, and this moves on, and I'm okay with this. Like,
check, yeah.
We lose my point of view when I die. Or I will lose my point of view. Like, other people don't have my point of view to start with, right?
But the information associated with it, or the correlations associated with it, in some sense, sort of will survive you. Or
like in the sense that I remember my grandmother as if she was here, right? And her actions have still an influence.
Yeah, that's beautiful.
In my life, and it's
beautiful. It's beautiful. Yeah,
but I'm lucky in having the kind of brain that is okay with this belief, right? Many people cannot help it, and and you really need something else to comfort you. And it's just good to be aware of like, what tools am I using? Yeah. To comfort myself, and is this also influencing my work, which is okay. I just should
be aware of it all.
This. Yeah.
Wow, it gets so subjective, but in a sense that how to put it is, I think closer to truth than thinking that there's this objective way to go about here. I agree with you that I also think I'm more inclined to thinking that I play this role that I don't understand yet, and I might dissolve, but it has had its function for the whole. What it makes me think is that we're talking about Heisenberg gut and what's quantum and what's classical, but as persons we also are making this gut, right? This is the gut I place sort of literally here, and that's my gut. And I just think that it's all classical, or say I'm quantum and you're classical. How can I know? But hearing you, and if there's no objective way to make that gut also sort of feels very human and humbling, that I cannot know sort of the larger whole I'm a part of, right? And that the cut I make is very subjective, even though I experience it to be very real. That's what it sort of is telling to me. Yes.
Also, like the boundary between what is I. I mean, I is a convention, right? That I say, okay, maybe like there's feelings in this body. This is where I cut it. And but this is a convention, and there's been others throughout history, and and it's something that we use for, I don't know, for applying responsibility, or for punishing people, or rewarding people, or for whatever. That has some social function, right? But it's this boundary is in principle like motel, and it's just where we put it.
And it's just super cool that you're working on modeling sort of that all, right? We are later this year, we will host a conference together where you are also involved and co-organizing with us on integrated information theory, which is also a theory that tries to model the boundaries of consciousness, or sort of where a whole, sort of a conscious whole, how we can sort of map that. And that I think is pretty cool, that we can sort of say something meaningful about how at least people experience being a conscious unit, so to speak. And I'm still puzzled, and this is also science fiction. I mean, I spoke to Christoph Koch, who says, okay, when you get to sort of a new maximum integrated information, so he said, if I connect the brains of the two of us, and you get to this maximum of new integrated information, there will be a new subject, and it will also that both Lydia and Hans at that moment cease to exist, and you have this one bigger brain. So that might be true, but it also might be true that perhaps the bacteria, the cells in my bodies have some form of consciousness that I'm not aware of, and I'm just experiencing this whole larger meta consciousness. These are all sort of the questions that I'm very much open to, and I just think it's cool that we now are finding ways or trying to explore it, right?
Yeah. It's cool.
Yeah. Okay, Lydia, thanks so much for this conversation. I really enjoyed it, and I really like how we got from quantum computing and these thought experiments to sort of more questions about the meaning of life. So just thank you very much. It's great for Essentia to have you as a research fellow working on all of this. And we have much more content also with you interviewing with me people we visited in the Vienna Foundations of Physics conference. And we will, of course, have a conference on IIT later this year. So there's more content with you coming up. And for you watching this, we will put in the descriptions below links to papers of Lydia and the scientists and physicists she referred to. And please leave questions, because Lydia and I will be filming more this year, so we can touch upon your questions and try and answer them. Thanks so much for watching.